Hi and welcome back. My name is Renee Clary and today we will investigate earthquakes. Earthquakes provide great evidence for the theory of plate tectonics, one of our major themes in geology. Let's get started. Earthquakes are defined as vibrations of the earth caused by a sudden release of energy and usually as a result of faulting, though not always. Magma movement within the magma chamber up through the pipe can also cause earthquakes, and monitoring of earthquakes in active volcanoes is really beneficial and alerts scientists to potential eruptions. Aftershocks are adjustments along a fault after an earthquake event, and foreshocks can be defined as those smaller adjustments that occur before a major earthquake. Why do earthquakes even occur? Well, the elastic rebound theory tells us that when the strength of rocks is exceeded, rocks will snap back to their former shape. And I have a little demonstration to show you. Here's a plastic knife, and as you note, I can bend it, but there comes a point when I bend it a little too far. Eventually, this one is not behaving. There we go. And it snaps back to its original shape. Now, the original shape is now in two pieces, of course, because I exceeded the strength of the rocks. So, diagrammatically, here we have in the upper left an original position of a fence and a fault running through it. Over time, deformation will see both sides of that fault moving past each other in opposite directions. Now, over time, the rocks may bend if the force is applied slowly, but eventually we exceed the strength of those rocks, so they snap back or rebound to their original undeformed shape. We see that the fence has now been offset. After rupture, the rocks will rebound or snap back to their original shape. Here's a great photograph. This is a displaced fence as a result of the 1906 San Francisco earthquake. No, the former was not intoxicated when he constructed that fence. It was originally in a straight line, but movement occurred along the fault. The rocks snapped back to their original position, and we had rupture at the point of that fence. This is known as a right lateral fault. And how do we know that is a right lateral fault? Picture yourself on either side of the fence. Stand on the fence, look across the fault or where the rupture occurred, and see where the fence is on the opposite side of the fault. Try it. And you will see that the fence has moved to your right, no matter which side you're standing on. That is known as a right lateral fault. To study earthquakes, we need some basic terminology. Seismology is the study of earthquakes, and a seismograph is an instrument which measures earthquakes. It produces a seismogram. The focus is the point where the earthquake originates or where the rocks actually rupture. However, commonly reported in the media is the epicenter. This is the spot on Earth's surface that is directly above the focus. So the focus may be several kilometers below Earth's surface, but the epicenter is commonly reported, and that's the spot directly over the focus on the Earth's surface. This is the rotating drum of a seismograph. And a basic setup of a seismograph, of course we have a lot of computer instrumentation, but here we have a device anchored to bedrock, and we have a suspended mass on a cable, so whenever the bedrock shakes, the suspended mass will move because of inertia, and the mass is connected to a marker on a rotating drum which records any type of movement. Here we have different seismograms. This represents the Taiwan earthquake of 1999 as recorded in California. And if you look at the top and you see the major movements over to the right, that is the earthquake. We have background noise, but the earthquake results in those major movements of the pin on the seismograph. Now, note the rocks may rupture below the surface, and here we see a focus with the earthquake energy or waves radiating out from the focus, but directly above the focus on the Earth's surface is the epicenter, and often news media will refer to an epicenter. Look at those waves radiating out from the focus. They are of varying types. Basically, there are two types of seismic waves. There are body waves which travel through the earth and surface waves which travel naturally on the surface of the earth. We can further subdivide each wave type into specific movements. Again, and I need to stress this, the two basic types of seismic waves are body waves and surface waves. The two different types of body waves are P waves or primary waves and S waves, secondary waves or shear waves. P waves or primary waves are the fastest. They move the fastest through the earth. They are the first detected at the seismograph. They are push-pull waves, and I'll demonstrate that in just a minute. The other type of body wave we're studying is the S wave, or the secondary wave. This is a shear wave, and the wave will actually vibrate or move perpendicular to the line of travel. Again, I'll demonstrate that in just a minute. S waves cannot be transmitted through liquids, and that's going to be a little important later on when we study the Earth's interior. Here we have a diagrammatic representation of a primary wave. This is a compression wave, and you can see in the blocks, the lines running through that wave, you can see areas where the lines are closer together. This is areas of compression, and areas where the blocks are now farther apart. This is an area of expansion. So note that the compression and expansion are working in the same plane as the direction of the actual wave movement or the propagation of the wave. Again, compression and expansion of the wave are in the same direction as the wave propagation. And let me show you that with a little demonstration. Okay, I have a slinky, and if I hold one end and the other, and I'm going to propagate my wave starting with my right hand over here. And note what happens to the springs. As I push in, you'll see the compression move along the surface of this wave. Let's try it. Did you see that? Let's try that again. Okay, I'm going to push in, and what you'll see are areas of expansion moving, and the movement of the wave itself is from my right hand to my left hand, so it's moving in this direction. Okay, let's do that again. Did you see it? One more time. Okay. Now, if we look at an S wave, it's not going to be in the same, the movement of the wave is not in the direction of the wave of propagation. Let me show you that real quick using the old rope trick. Okay, I'm going to stand for this one over here to get out of your view. And basically, this is the old jump rope trick that we did in grammar school, where we make the snake. If I'm over here and I'm going to flip it, and you're going to hopefully see the wave propagate across. Okay, let's try that again. Okay, so again, the wave movement, the actual movement of the rope was in the up-down direction, but the direction of propagation was from my right hand toward the end of the table. Okay, let's move back to the slides. Whoops, got that fast finger again. Okay, this is the block diagram representing a secondary wave, and you can see that again the movement of the material is in the up and down direction, but the propagation of that wave is actually moving from the left to the right. So the movement is perpendicular or shear to the direction of the wave propagation. So that is a secondary or shear wave, and it's not as fast as a primary wave. Primary waves arrive first at our seismic stations. Now, the two types of waves again are body waves and surface waves. Surface waves travel on the ground, and as you might suspect, there are different types of surface waves as well. We have Rayleigh waves, which are slower, and they move, sort of propagate like water from a central point and radiate outwards. Love waves have a lateral motion back and forth, and they can be very, very damaging to foundations. Diagrammatically, we see a Rayleigh wave here, or an R wave, and you can see that internal rotation of material. It's like a water particle, and that is discussed in the lecture on shorelines. We look at wave propagation there. But Rayleigh waves behave very similar to water waves. In the 1990s, outside Mexico City, eyewitnesses reported actually seeing the earth move as these huge swelling waves across the ground. So these eyewitnesses were observing Rayleigh waves. The love waves, on the other hand, have a lateral back and forth motion, side to side motion, and you can see the disturbance there in that block diagram of the material. So this is very, very damaging to foundations. It's a back and forth, and it can reverberate a lot, especially in unconsolidated sediments. Now, how do we locate an earthquake? We actually need 3 seismic stations. We need 3 locations where the primary and secondary waves were measured. And we draw circles whose radii is going to correspond to the distance between S and P wave arrival on a time distance graph. I'll show you this in just a minute. So the intersection of our 3 circles is going to be an epicenter. That may be a little confusing. Let me try to clarify that. Okay, so we can tell how far away an earthquake occurred by the difference in the different earthquake wave arrival times. So P waves travel fastest, right? Let's consider an analogy. Let's say you're tall, 6 foot 4 inches. So you have a long stride. I'm only 5 feet 3.5, maybe 4 inches on a good day. Okay, we're both going to start walking from your house at the same time. You're 6 foot 4, I'm 5 foot 3.5. We're going to walk towards the big box store 3 miles down the road. If we start walking at the same time, you obviously will cover more ground than I will. You'll have a longer pace. Perhaps after 5 minutes, you may be 50 feet ahead of me. If we keep walking, after 10 minutes, you may be 50 feet ahead of me. So 20 feet, 50 feet, the distance will keep growing as we walk. You walk fastest, so after 5 minutes, you're X feet ahead of me. After 10 minutes, you're more than X feet ahead of me. So the distance will continue to grow. And if we know the time of arrival between the primary and secondary wave on the seismogram, we can tell how far away that earthquake was. Here's the PS arrival time on that seismogram. Now, we can look on a graph. Of course, this is all computerized now, but we can take that primary, secondary time interval and locate the distance, how far away that earthquake was. So we know the time difference, we know the rates of primary and secondary wave travel, so we determine the distance. The problem is, in which direction? We can plot the distance, but we have no idea in which direction the earthquake originated, so the earthquake focus can be located anywhere along a circle, and that's why we need more than one seismic station. What if we only had 2 locations? What if we use the Berkeley station, and that is symbolized by that blue circle, and we use the Denver station, and the Denver station is shown in that orange circle? What if we use those 2 seismic stations? Well, we have possible locations along a circle from Berkeley and possible locations along a circle from Denver, so we actually end up with 2 possible locations for that earthquake where they intersect. So we need 3 seismic stations. If we add a 3rd seismic station, in this case we're going to look at New York, then where all 3 circles intersect, we can actually pinpoint the focus, and it's down there in Mexico. So how do we measure earthquakes? We can locate them with 3 seismic stations, but how do we measure We measure earthquakes on the intensity as well as the magnitude. Let's look at the intensity first. Now, these are totally different scales. If we look at the intensity, we use the modified Mercalli intensity scale. This is a qualitative scale, which means that it is slightly subjective. It measures the intensity and the kind of damage done by an earthquake, and an earthquake is assigned Roman numerals from 1 to 12. What do I mean by qualitative or subjective? How many of you watch the Olympic Games? If you watch ice skating in the winter or the diving competitions in the summer, you'll observe judges posting scores. There are always several judges, and it's rare that they all agree on the score. Now, each judge has the guidelines and what qualifies as an excellent dive or an excellent movement on the ice. However, there's some subjectivity in assigning the score. It is qualitative, the same as the modified Mercalli. The intensity, the scale, what is rated, the earthquake is rated, is affected by the amount of energy released by the rupture, the distance of any location from the epicenter of the earthquake rupture, the focal depth, how far below the surface did that earthquake rupture, the further down, the deeper it is, generally the more dissipation of the earthquake waves before the surface. So shallower earthquakes tend to cause more damage as a rule of thumb. The population influences the rating of the intensity scale. How many people were affected? The local geology is very, very important. What types of rocks? Unconsolidated sediments are particularly bad for liquefaction. Bedrock is much better. The type of construction, earthquake buildings that have been constructed especially in zones where there is high earthquake activity tend to fare better than brick buildings that are not reinforced, or buildings constructed of mud with no reinforcement whatsoever. The duration of the shaking, how long the shaking continued, how long the rupture fault was, all affect the modified Mercalli intensity scale. This shows you some of the ratings and some basic guidelines for assigning those ratings. For example, if you look at 2 is felt only by a few people at rest, maybe taking a nap, especially on the upper floors of buildings where the sway would be greater. On the other hand, look at 10. Some well-built wooden structures are destroyed. Most masonry and frame structures with foundations are destroyed. The ground badly cracked. So there's a lot of difference between a Mercalli 2 and a Mercalli 10. Again, there is some qualitative subjectivity in assigning this scale number, but there are guidelines, and here are just some basic overviews of the guidelines. They are much more detailed in other documents. This diagram shows the intensities of the 1906 San Francisco earthquake. The darker areas up at the top have the higher Mercalli intensities, and here at the top we are looking at areas underlain by bay mud, and these are unconsolidated, so they tended to have more damage than the green areas. The green areas tend to correspond with bedrock, so these areas experienced less damage because of the underlying geology. In the earthquake, in the 1906 San Francisco earthquake, the intensity of the earthquake was very strongly correlated with that underlying geology. Now, what about magnitude? Magnitude is not intensity. We are looking at measuring two different things with two different scales. Most commonly, you will hear about the Richter magnitude scale. This is a quantitative scale. It measures the earthquake magnitude, and it's based on the amplitude and the distance and the total energy released from the earthquake, from the rupture. What do we mean by quantitative? Let's go back to our Olympic game analogy. If you are watching in the Summer Olympics, for example, you see a runner or a swimmer simply racing the clock. The process is precise. The winner of the race is not often debated unless there was a problem in perhaps unfair conduct or jumping off the block too soon. The person is simply racing the clock. So it is not subjective. It's a measurement by an instrument. Human subjectivity is not involved in a quantitative measurement. The Richter scale is logarithmic, which means that each number increase from 7 to 8 would mean 10 times more wave amplitude. So an 8 earthquake on a Richter has a 10-time greater wave amplitude than a 7. Now, this doesn't correspond as a logarithmic scale for energy. Energy is about 30 times more per each number increase. We see 7 to 8 major earthquakes a year, minor earthquakes 3 to 4, hundreds per day for these little bitty minor earthquakes. Excuse me, I said that incorrectly. Major earthquakes we're looking at 7 to 8 on the Richter magnitude scale, whereas minor earthquakes are 3 to 4 on the magnitude scale. But we see hundreds of these little minor earthquakes per day. So minor earthquakes are much more prevalent. The major earthquakes, we don't see many of these per year. This is how we determine the Richter magnitude. We're looking at the amplitude of the recording by the seismograph, and that is shown in the upper right hand corner. Let's try an example with this. Let's say that in California, the Los Angeles area just experienced a magnitude 8 earthquake. That would be devastating. How would this compare with an earthquake of magnitude 5 that occurred in Alaska last week? Well, the intuitive thing to do is just to say that 8 minus 5 is 3. Oh, that's 3 times bigger. That's not how it works. Remember, the difference in magnitude from 5 to 8 is 10 times 10 times 10. Each number increase is 10 times an increase in wave amplitude. So the California earthquake would have 1,000 times greater wave amplitude than one in Alaska of magnitude 5. What if we look at the energy? If we look at the energy, we're looking at 30 times 30 times 30, or 27,000, I have an extra zero there, sorry, 27,000 times more energy released between a magnitude 8 and a magnitude 5. The thing to keep in mind here is that we're going up logarithmically with a wave amplitude, so each number increase is 10 times greater as far as wave amplitude. And when we look at the energy released, we're actually looking at 30 times the amount of energy increased with each number increase. So earthquakes on the Richter, the higher the number, the much more devastating the result can be, because we're looking at a lot more energy than the lower number Richter earthquakes. Commonly now you'll see something known as a seismic moment magnitude. This is also a quantitative scale, but it takes into effect the earthquake strength, the length of rupture, and the movement of the rocks adjacent to the fault. So we can locate earthquakes, we can measure earthquakes. What are the effects of earthquakes? The most obvious one is ground shaking, and it has been said that earthquakes don't kill people, falling buildings kill people. So if you're out in an open field and the ground starts shaking and you fall down to the open field, nothing serious is going to happen. You'll feel the ground movement, but you will not be threatened by any falling buildings or any type of activity that you would find in a city. However, the secondary effects of earthquakes can be pretty severe. Solifluction, liquefaction can occur, where the sediments below the surface act like a liquid. Slumping can take place. Landslides can occur. the underlying geology strongly influences how the rock reacts. So solid bedrock versus unconsolidated sediments, for example, if we look at this diagram, we see that the wave is moving from the left to the right at the bottom. The bedrock will transmit that energy very, very efficiently. Now, we can get into well-consolidated sediments, and you'll note that the amplitude is increasing of that wave. It's slowing down. The energy is getting trapped in the sediments. Poorly consolidated sediments and bay mud and water, particularly, the energy of the earthquake gets trapped and sort of reverberates around in those sediments, and that can result in solifluction or liquefaction, which can have devastating effects on the land and the people who live right above it. This diagram shows shaking amplification, and you can see along the bay extremely high, black. The very high are in that dark brown. And again, this is reflective of the underlying geology with the unconsolidated sediments. When you look at blue, the low areas, you're looking at bedrock. So the wave passes through the bedrock very efficiently, but structures on bedrock fare a lot better than structures that are on unconsolidated sediments. Even earthquake-prone structures or earthquake-resistant structures are not totally resistant to earthquakes. This is the Nagita, Japan earthquake of 1964. The buildings were constructed according to guidelines for earthquakes. However, the land beneath the buildings experienced liquefaction during the earthquake, and you can see that the buildings are displaced. They seem to be held together, but they're no longer in an upright position. And waves, of course, as you might suspect, will affect building structures, different types of building structures in different ways. And this shows the effects of ground shaking on tall buildings of different shapes. And you note that rupture usually occurs along the point where the wave meets, or where the building is shaking, and a wave can split, or as a wave moves up a tall structure and then starts reversing and coming down the structure, where the waves meet, you tend to get rupture of a building. Here's a great photograph, unfortunately, a great devastation of Northridge, California. This is a parking structure in 1994, right after that Northridge earthquake. This photograph, also taken at the time of the Northridge earthquake, shows how basically those concrete, reinforced rebar concrete pillars just blew out. And what probably happened here, again, remember that earthquake wave can travel up that structure, and then the wave will also reflect and travel back down. And when the upcoming wave meets the downcoming wave, you tend to get a huge rupture area. There we go. Here's slumping after the 1998 Afghanistan earthquake, ground failure. And the very classic 1906 earthquake in San Francisco resulted in a lot of damage as well. Here's some early photographs documenting the devastation in the area. Complete rubble. Now, in addition to the ground shaking and ground failure, there are other effects of earthquakes that individuals need to be concerned about, especially if they live in areas that are earthquake prone, or if they live in areas near the sea. And those are fires that can break out because of ruptured gas mains and tsunamis. And tsunamis are seismic sea waves. We'll look at those in a little bit more detail. Let's move back to that 1906 San Francisco earthquake, and you can see San Francisco in flames. Again, when you have rupture of gas mains or different flammable materials, the problem is not only the fire, but the earthquake has most likely destroyed conduits for water. So fire departments have a pretty difficult time in getting water to put out these fires. The newspapers, of course, in 1906 reported the devastation of San Francisco. There was some political effort to keep that news down. California was a growing state, and settlers were encouraged to come in and make their living and become rich. And of course, that 1906 San Francisco earthquake didn't help matters. So there have been accusations of doctored photographs where the devastation was made not to look as bad as it was. Fires, of course, have happened in other earthquake events. This is Balboa Boulevard in flames during the North Ridge earthquake of 1994. This was the result of a ruptured gas main. Tsunamis. Tsunamis are seismic sea waves. They're not tidal waves. They are caused by the sudden slumping of material or the displacement that results from an earthquake that occurs in a large body of water or adjacent to a large body of water. And the key for a tsunami is displacement. The water has to be displaced either by a large amount of material moving in to the water basin, or faulting where the seafloor is disrupted and one area is uplifted. So there has to be water displacement. The December 26, 2004 Indonesian tsunami claimed over 212,000 lives. I think the current estimate on that is over 220,000 lives. But just to show you just how devastating these tsunamis can be, this is a photograph of Banda Aceh in Sumatra, Indonesia, taken in June of 2004. And this is the same area 2 days after the tsunami. Let's look at that again. Before and after. Unbelievable devastation. Why is it so devastating? In open water, if we have a displacement, and you can see in the lower right of that block diagram, a displacement on the seafloor, the area on the right is uplifted, and that displaces the water. And this energy will travel across the open sea. Now, in the open sea, because the basin is deep, you really don't notice it. And ships at sea might not even notice the individual waves associated with a tsunami. However, as that wave approaches the shore, look what happens to the seafloor. We are now moving from the deep seafloor up a continental slope and rise, and that energy, the movement, the rotational movement of the water is disrupted. So the energy is transformed and translated upward, and that's what will create these huge waves that crash into the shore. This might be a little bit better diagram of that. Notice that the tsunami in deep water, the wave may only be 20 inches or 1.6 feet tall. And the speed, though, is incredible. It's 450 to 650 miles per hour. Compare that with a regular wind-generated wave, and a wind-generated wave can be 10 to 20 miles per hour, and it can be up to 10 feet high. So you won't notice that tsunami in the deep ocean. 20 inches? Compared to a wind-generated wave of 10 feet, not very noticeable. But as that tsunami approaches the shore, the speed can be anywhere from 30 to 200 miles per hour. It does slow down. The base of that wave will interact with the seafloor, and the energy is translated up. And now we have a wave that can be 100 feet or more, 5,000 to 10,000 feet across. So huge waves result from the displacement. This diagram shows the tsunami travel times around the Pacific to Honolulu. Honolulu, Hawaii, the Hawaiian Islands have been, unfortunately, the recipient of many tsunamis over the years, and there is a tsunami warning system. If something, for example, slumps or faults over on South America's the side of the western side of South America, we can have a good 14-hour advance notice to warn the residents of Hawaii to move to higher ground. If an Alaska earthquake, though, would generate a tsunami, there is less response time. So the tsunami warning centers are aware not only of the occurrence of the earthquake, but the generalized speeds at which they travel across the Pacific Ocean. Here's a tsunami that hit Hawaii in the 1940s, and there is an individual there in the lower left. There he is, getting ready to be swept away by the waves. A classic photograph, a tragic photograph, showing the devastation that resulted from this tsunami. 1946, another Hawaiian tsunami. The boat is not normally docked there. This is an overview of Hilo from the 1960 tsunami. The tsunami was generated by an earthquake on the west coast of South America. The tsunami warning system was not in place, and you can see the devastation that resulted. Where do earthquakes occur? As you might suspect, they are closely tied with plate tectonics, and earthquakes provide great evidence for the theory of plate tectonics. 80%, that's a lot, 80% of all earthquakes occur in the circum-Pacific belt, same thing as the Ring of Fire with volcanoes, and these occur along convergent plate margins. 15% of earthquakes occur in the Mediterranean Asiatic belt, and we see 5% that are scattered, some within plate interiors. The famous 1811-1812 earthquakes that occurred in New Madrid, Missouri, or in a continental interior. It is hypothesized that these earthquakes occur along an alocogen that is now deeply buried below the surface. An alocogen, you may remember, is the failed arm of a rift. When divergent plate boundaries begin, we have a triple point junction, and spreading will continue along three arms, and one of them eventually fails. And it is hypothesized that the New Madrid earthquakes are the result of movement along that old alocogen from the breakup of an old supercontinent. This map shows the location of different earthquakes around the world. The red dots mark what are known as deep focus earthquakes. These are associated with convergent plate boundaries, specifically subduction. Divergent margins and transform margins can produce shallow earthquakes, and these tend to be, again, a little bit more destructive. The energy is not as readily dispersed before reaching the surface if the focus is nearer the surface. And here we have a subduction zone. We have convergent plate margin where the oceanic plate is being subducted underneath another oceanic plate. And deep focus earthquakes can occur along subduction zones such as these. Here's another diagram that shows the earthquakes on the subduction zone. Again, we're moving pretty far beneath a continent, even if we have an oceanic continental convergent plate boundary, and earthquakes can be generated all along that subduction zone. The shallower transform faults that generate the earthquakes tend to have more devastating earthquakes because the energy is not dispersed before reaching the surface. The rupture occurs relatively near the surface. The famous transform fault of North America, of course, is that of the San Andreas. You can see, though, that California has a lot of faults that run through the state. Here is an overhead shot of the San Andreas Fault at the Crystal Springs Reservoir. You can actually see it move across the land. Here's the Point Reyes view of San Andreas. Okay, so Californians are very well aware of what lies underneath the surface in their backyards. How can we predict earthquakes, mitigate earthquake damage? We use what are known as seismic risk maps, and these identify seismic gaps. Along a fault, we have regular movements of different individual segments. Some areas, however, are known as locked, and there has not been movement, and there hasn't been any small quaking or any small movements to dissipate some of that locked energy. So it is predicted that in these seismic gaps, major earthquakes can occur, and they're predicted to occur more readily than, let's say, an area that has experienced a major earthquake and isn't one that undergoes an earthquake every 5 to 10 years. This is a global seismic hazard association map, and note that much of the seismic hazard is centered on the circum-Pacific belts. Also, you can see India, the continental convergent plate boundary there. We have India moving up into Asia, and a lot of earthquake hazards associated with that as well. Let's go back to California. If we look at the San Andreas, note we have a pretty good seismic gap here along this segment. We haven't had earthquake activity, which is symbolized by those little tiny blue dots. So we haven't seen any earthquake activity in the center of that red circle. So that might be an area that scientists hypothesize might see a major quake in a nearer term than an area that has lots of these little blue dots and has been relieved of energy through more frequent earth movement. Look in the Loma Prieta area. You see before the Loma Prieta faulting in 1989, we had some seismic gaps, and then down below, now we filled in that gap. In addition to seismic risk maps, elevation changes or tilting of the land can indicate an impending earthquake rupture. Water level change in wells can also indicate earthquakes. We used to note that perhaps animal behavior did predict earthquakes, but there is no accepted scientific study that documents this. So although it is hypothesized, the jury's still out on that one. There have been instances where animals have appeared to note earthquake movements or impending earthquake events, but there is little scientific data to back that up. There is a lot more data that suggests that perhaps there is no correlation. So how do we control earthquakes? If we can predict them, can we control them? Well, interestingly enough, the idea has come about, the hypothesis has come about that we should perhaps pump fluids into seismic gaps. Why? Perhaps to lubricate that fault and to allow small slippage in order to alleviate some of that energy, dissipate some of that energy, and avoid a big event. Now, where did that come from? Okay, this is a neat bar graph, and up at the top we see in purple earthquake frequency, and below that the bar graph is contaminated waste injections. So when contaminated wastewater was injected at the Rocky Mountain arsenals, and it was injected at about 3,700 meters below the Earth's surface, the Denver area experienced numerous small earthquakes. And this is an oddity because Denver is not an area that is earthquake prone. It was really rare for them to experience earthquakes and this many earthquakes. And notice that when the injection ceased, that gap in the lower diagram, look what happened to the earthquake activity. It greatly diminished. Now, the question becomes, if this works, if we can inject fluids along fault zones and stir movement, perhaps a little bit of movement to ease the energy, that locked energy, would you take that risk? If you lived along the San Andreas Fault, would you want to inject wastewater in the fault near your home? Of course, it may alleviate some of the energy and dissipate some of that energy that's locked in the fault. Of course, it may also spur the big one. So thus far, there's a lot of debate and not a whole lot of consensus on whether or not this can be used effectively to sort of alleviate and control earthquakes. Well, that will mark the end of our video discussion on earthquakes. Thank you so much for joining me. If you have any questions, please feel free to post them on your discussion board or email your instructor. Thank you so much, and I'll see you next time.